In the last two videos, we followed a strange journey. The Greeks were studying circles, using chords to track the motion of the heavens. Then in India, Aryabhata changed the perspective. Instead of chords, he measured the height of a point on the circle from the diameter, what he called jya, and what we now call the half chord. But something is missing, because today trigonometry isn't about circles, it's about triangles. So the question is, where do triangles come in? Let's go back to the circle. Take a point at some angle and draw the radius to that point. Now, drop a vertical line to the diameter. Suddenly, we have a right triangle, and Aryabhata was trying to measure the height of this triangle. But we still seem to be missing something. Here's the key idea. If we make the circle bigger while keeping the angle the same, the triangle gets bigger, but its shape doesn't change. That means all these triangles are similar, and because they're similar, the height always scales in the same way as the radius. So the height must be proportional to the radius, which means we can write the height as radius r times some factor. Now, if I move the point higher up on the circle, while keeping the radius the same, that is, increase the angle at the center, the height increases yet again. So the other factor must be dependent on the angle. But we can't just multiply the radius with the angle. So we define a function of the angle, which returns some value that makes sense. A function is a rule that takes an input and produces an output. For now, we don't need to worry about the rule. Just that for every angle, it gives us a consistent value. So you get height is equal to r times some function of the angle, theta. Now, if you divide both sides by r, you get the function of theta is equal to the height divided by the radius. The function of the angle can now be represented as a ratio between the height and the radius. And that function is what we now call sine. Let's take a closer look at the triangle. The radius is the longest side in a right triangle, so it's the hypotenuse. The height is the side opposite to the angle we're looking at, so it's the opposite side. The base of the triangle is the side that's adjacent to the angle, so we call it the adjacent side. So this ratio becomes sine of theta equals opposite over hypotenuse. And just like that, trigonometry becomes about triangles. We can define two more ratios in the same way. I haven't talked about cosine or tan in the first two parts because they didn't have much physical significance. Sine, the height, is how far up something is in the sky, and that is measurable and useful in astronomy for predicting celestial movement. But the horizontal distance, the complement to sine or cosine, wasn't directly observable in astronomy, so it wasn't as central as sine. Tangent was important in practical settings, like measuring shadows and heights, but it wasn't the central quantity in early astronomy. Over time, it became a way to show the slope of a line. We now define cos as a base divided by the radius, or adjacent side over the hypotenuse, and tan as the height over the base, or opposite over adjacent. These ratios don't depend on size, only on the angle, and that's why they work. But this raises a question. If sine is this ratio, how did people actually find its value? Initially, values were computed using geometry and interpolation, building large tables of sine values. In the 1300s, an Indian mathematician and astronomer called Madhava discovered that sine could be calculated for any angle using this infinite series. You could generate sine for any angle just by computing a few terms. However, the angle has to be in radians, which I'll cover later in this video. This meant sine could be calculated directly from a formula rather than built step by step from geometry or tables. I'll go more in depth into these infinite series in part 3b of the series. So we've simplified trigonometry to triangles and functions of the angle, and found values for those functions. But there's a problem. Right triangles only exist for angles less than 90 degrees. So what does sine of 120 mean, or cosine of 200? There's no way to form a right triangle with those angles. The triangle definition breaks. If we want trigonometry to work for all angles, we need to go back to where it all started. A point moving around a circle. But now we add something new, direction. We introduce axes. Right and up are positive, left and down are negative. Now every point on the circle has a position, a horizontal value and a vertical value. And here's the key shift. We're no longer just measuring lengths, we're measuring displacement from the center. If the point is to the right, the horizontal value is positive. If it's to the left, the horizontal value is negative. If the point is above, the vertical value is positive. If it's below, it's negative. We still define sine and cosine the same way as before. Sine is a vertical component, cosine is a horizontal component. The radius stays positive, it's just a distance. But the horizontal and vertical components can now be positive or negative, depending on where the point is. So when the angle passes 90 degrees, nothing breaks. The point simply moves to the left side of the circle. So the horizontal component becomes negative, and the vertical stays positive. And as it continues, both sides can change. That's where negative values come from. Not from changing the definition, but from allowing direction. And because of that, sine and cosine can now work for any angle, not just inside a triangle, but anywhere on the circle. This holds for any circle, but every circle is just a scaled version of another. So instead of carrying around that extra scaling factor of r, we choose the simplest possible case, a circle of radius 1. And when we do that, the geometry itself becomes a function. The height becomes just sine theta, and the base becomes just cos theta. We're no longer measuring lengths, we're describing position. But there's one more step. How do we actually measure the angle? Up to now, we've been using degrees, but degrees are arbitrary. There's a more natural way to measure angles. Radians. Imagine walking along the edge of a circle. If the distance you walk is exactly equal to the radius, then you've moved through 1 radian. So radians don't actually measure rotation in an abstract way. They measure how far you've actually traveled along the circle. And on the unit circle, where the radius is equal to 1, the angle becomes exactly equal to the arc length. So, as a point moves around the circle, the angle directly measures distance traveled. Just like Aryabhata choosing a radius of 3438, so that arc length closely matched angle in arc minutes. Radians make that relationship exact. Now, here's a key insight. A full circle has a circumference of 2 pi. So, how many radians are in a full circle? Well, we're asking how many radius length steps fit into the circumference. Well, that's 2 pi times r, the circumference, divided by r, the radius, which gives us 2 pi. So 1 full rotation is 2 pi radians. And that gives us a natural way to convert between degrees and radians. A full circle is both 360 degrees and 2 pi radians. So 180 degrees is pi radians. From this, we can convert between the two. Multiply degrees by pi on 180 to get radians, or multiply radians by 180 on pi to get degrees. But the real point isn't the conversion. It's that radians connect angles to geometry and to motion in the simplest way possible. And now everything comes together. What began as chords in a circle became heights, then ratios in a triangle, and finally functions that describe motion itself. In part 4, we'll explore the relationships between these functions, the identities that tie all of trigonometry together. That's it for this video. Thanks for watching, and I'll catch you in the next one.